Let's find out time period of a simple pendulum. What is a simple pendulum? Simple pendulum means you have a point mass, and this point mass is connected by a massless rope. Well, it's not a point, but just consider this thing as a point. This is ball as a point, and this rope is massless. If you have a massless rope and a point mass is connected to it, then when it oscillates, this is called a simple pendulum, and we need to find its time period. Now, how do we find this time period? This is the rope of length L, and at this end, remember we have a point mass. This is the point mass M. It is going to oscillate between these boundaries, and oscillations are like this. It's going this way, then it comes and moves in this direction. That's how it oscillates. This is called a simple pendulum. If you have something like this, a marker, mass is present everywhere as a rod. When you oscillate something like this is called a compound pendulum. Steps for finding time period, they are exactly same. Understand this and you can find time period of something like this, which is called a compound pendulum. Now, first thing which you notice in this figure, which is different from these oscillations which we have already done, we have found time period of a spring block system. M, K, and we found that time period is coming 2 pi under root M by K. This is something which we have already done. K is your force constant. This M oscillates like this. Now, I hope you notice the difference between these oscillations and these oscillations. Look at this. And look here. This is called linear SHM. Linear simple harmonic motion. For linear simple harmonic motion, we use A equals to minus of omega square x. A is your acceleration, displacement from the mean position. What is the mean position? Mean position is that position where total force is what? 0. Now what are these? These are angular oscillations. Remember I said angular oscillations. You will see when this thing becomes angular simple harmonic motion. These are angular oscillations. You have angular amplitude theta naught. In this, we define this as capital A. Amplitude, linear amplitude is capital A. This is your angular amplitude theta naught. So displacement, it becomes angular displacement when you talk about angular motion. Now, for angular SHM, for angular SHM, we must have this equation. Look at the similarity. We have done these things in rotational motion also. Acceleration, it becomes alpha, angular acceleration. Omega is same. Remember, it is angular frequency. Displacement, it becomes angular displacement. So this is your angular acceleration. And this theta is your angular displacement. If something, when it oscillates and satisfies this fundamental equation, then we say that those angular oscillations are basically angular simple harmonic motions, oscillations of this type. Now, when we write A equals to minus omega square x, once we have got omega, we write omega as 2 pi upon t, and then it gives us what? Time period. For omega, we have to write this equation. And how do you find acceleration? With the help of force. When you divide force with mass, you get what? Acceleration. So how do you get alpha? For alpha, we write torque, and then we divide torque with moment of inertia. Again, similar steps. How do you find A? Acceleration is found with force divided by mass. Whereas in this case, F becomes what? Torque. Mass becomes what? Moment of inertia. If we can find alpha with the help of tau upon I, and if that alpha satisfies this equation, we have angular simple harmonic motion. We just need to find omega, the coefficient which is attached with this theta, and that will give us time period. Now look, how do we develop this torque part? Now, what is theta naught? I told you theta naught is the maximum angle which you produce for the pendulum. This is the mean position. Why is this the mean position? What do you mean by mean position? Mean position for linear SHM is what? That position where net force is 0. Whereas mean position for angular SHM will be what? That position where net torque is 0. In fact, write down this statement. For linear SHM, mean position is that position where net force is 0. Whereas for angular SHM, mean position is that position where net torque is 0. What is theta? What is x? Displacement from the mean position. What is theta? Angular displacement from the mean position. Write down this. Theta is angular displacement from the mean position. Also write down what theta naught. Theta naught is maximum angular displacement. Theta naught is maximum angular displacement from the mean position. That's the maximum. Now, if I ask you where is the mean position of a simple pendulum, then I hope you can see, if you hang the simple pendulum like this, you do not disturb it, it will remain like this only. That's the mean position. It is not going anywhere if you leave it like this. When you disturb it from the mean position, it has a tendency to move back towards the mean position, but by the time it arrives here, it gains some angular velocity and therefore it moves to this side and then comes back and we see what? Oscillations. That's your mean position. Mean position. From this mean position, if you displace your pendulum by an angle of theta, then at this position we need to find what? Torque. Once you find torque, divide that with I, find alpha. If you can have a relation like that, you will find the time period. How do we get that? Look here. Downward force acting on the ball is mg. And there is a tension force in the rope. Let's say that tension force is F. Instead of T, we are taking F because T we are using for tension force. So this is the F, tension force in the rope. These are the two forces which act on the ball when you displace it by some angle theta. Over here, this is the tension force in the rope. And downward force is what? mg. And we need torque about the point of suspension. This is the point of suspension about which you need to find torque. Now, how do you find torque? Torque is force multiplied by perpendicular distance of force from the axis of rotation. That's how we have defined torque. There are two forces, F and mg. What about torque of F? This is point of suspension, this is the axis of rotation. This is your body which is oscillating. Tension force is passing from the axis of rotation. If a force passes from the axis of rotation, you know that its torque is what? 0. And therefore, write down the statement. Since tension force F all the time passes from the axis of rotation. Tension force all the time passes from the axis of rotation. Its torque is always 0. Its torque is always 0. All the time means in this position, this hand represents the axis of rotation. Rope is connected to this point and therefore tension is passing from the point of suspension. If it moves here again, if it moves here again, if it moves here again. So torque of tension force is all the time 0. It does not give you any restoring torque. What about mg? Look at mg at the mean position. Right at the mean position, this is your mg. At mean position, this mg is passing from the axis of rotation. Force is passing from the axis of rotation and therefore it has no torque, but only at mean position. And that's how we define mean position. But once you displace it by this angle theta, this mg no longer passes from the axis of rotation it now develops its torque, and that torque tries to bring your simple pendulum towards the mean position. I hope you understand how these forces are working in this figure. So the only thing we need to find is what? Torque of mg. How do you find that? Look here. This is the axis angular position theta mg. This angle is theta. So you can do what? You can resolve this mg. This angle is also theta. Theta, this is also theta. What is the component of mg in this direction? Component of mg in this direction is mg cos theta. And component of mg in this direction is what? mg sin theta. These are the two forces acting on mg, on this ball, mg cos and mg sin. If I ask you what is the torque of mg cos, then you should say 0. Why? Because this mg cos is passing from the axis of rotation, and therefore it does not produce any torque. Torque due to mg cos theta is what? 0. And what is that force which is responsible for the torque? Only this component, which is mg sin theta. So on this body, on this ball, when you connect it like this component is mg sin theta and is producing what? Torque. The mg cos theta, what it does? Mg cos theta is trying to pull the whole thing along the length itself. It doesn't produce any restoring torque. It doesn't have a tendency to move this thing over here. What force has this tendency? This mg sin theta which you see is trying to move ball for the mean position, towards the mean position. Now, once you take components, how do you take components? This component, you know, is already perpendicular to this length. And what is this length? This length is L. And how do you define torque? We define torque as force multiplied by perpendicular distance from the axis of rotation. What is the force? Force is mg sin theta. That's your force, mg sin theta. And what is perpendicular distance of force? What is perpendicular distance of force from the axis of rotation? That distance is what? L. mg sin theta multiplied by L. That's your torque. mg sin theta multiplied by L divided by I, moment of inertia. Now notice one important thing. We will be using a negative sign. Why a negative sign? Look at the torque of mg. We have given an angular displacement like this. This is anti-clockwise angular displacement. But torque of mg is trying to move it like this. Torque of mg. Torque of mg is what? Because of mg sin theta component only, which is this. So you can see that when you displace your pendulum clockwise, anti-clockwise, mg, its torque is clockwise. So we are saying that angular acceleration is trying to restore. Negative sign means restore. Your torque or angular acceleration is trying to restore the system and therefore we are using the negative sign. Once we have the negative sign, what is this bob? This bob is what? A point mass. What is moment of inertia of a point mass? mr square. What is r? Perpendicular distance from the axis of rotation. What is perpendicular distance from the axis of rotation? L. And therefore your alpha, this alpha becomes minus of mg sine theta, mg sine theta into L divided by I, which is ml square. Once you got your alpha in this form, simplify the whole thing, and when we simplify this part, you see m cancelled, alpha is coming minus of g divided by L, g, L square cancel, m gone, sine theta. For angular simple harmonic motion, your alpha should be directly proportional to what? Theta. But this is what? Sine theta. So if I ask you at this stage, is it an angular simple harmonic motion? You will say no. This at this stage is only angular oscillation. This is not angular simple harmonic motion at this stage. But if theta is very, very small, you know that sine theta then can be approximated with what? Theta. And once you say that for small angles sine theta can be approximated with theta, let's put this thing over here and you get what? Alpha as minus of g upon L into theta, which is this. And therefore angular oscillations which are not simple harmonic, once you say theta is small, this also becomes what? Angular simple harmonic motion. So remember an important point. If they ask you that a simple pendulum always executes simple harmonic motion, answer is no. If angle is large, then this is not simple harmonic. Only when angle is small, motion is what? Simple harmonic. Remember this. In fact, we'll write the statement later, but let's complete the whole thing. And once you compare this with the fundamental equation, what is omega square? Coefficient of theta, G by L. G by L. This gives us omega as root over G by L. And what is omega? Omega is 2 pi divided by T, which gives us time period as 2 pi root over L divided by G. I hope you have seen this format. T equals 2 pi root over L upon G. This is time period of a simple pendulum. Now write down important point. Only when theta is very, very small, motion is simple harmonic. For large angles, motion is periodic, oscillatory, but is not simple harmonic. So remember the steps for this time period. For any system which oscillates and performs simple harmonic motion, these are the simple steps. Go and find the mean position. If it is linear, find out that position where net force is 0. If it is angular, find out that position where net torque is 0. Then if it is linear, find out A and relate that A with X, which is displacement from the mean position. If it is angular, then go for alpha. For that, find out torque. Divide the torque with moment of inertia and you will get what? Alpha. And relate your alpha with theta in this form. If you can do that, then that body or system will execute simple harmonic motion. Now, why I am saying this? If I ask you that we have a rod, I'm giving you this as a homework. If I give you a rod and I ask you that this rod is executing simple harmonic motion, find out its time period. Mass is m, length is l. Then I told you that this body is called what? Compound pendulum. Everything is same. Now look at the changes. For this ball, mg was acting at this position. But if you have a rod, your mg will act not at this point, but at this point, which is the center of mass. If it is the center of mass, then torque will be same, but instead of writing L, you will write distance of center of mass from the point of suspension. So if we have a rod, what is the length of center of mass? L by 2. You will write L by 2. And what about I, moment of inertia of a rod? What is moment of inertia of a rod? About an axis passing from the end. ml square by 3. Your I will be ml square by 3. Take small angles and you can find that time period. And then you can do the same thing for any body which is going to oscillate. Note down everything.